Okay, so I wrote on the table what I think was the main message of yesterday. So what I've tried to do is organize for you the flurry of groups which appear in the literature, and I feel personally it's sometimes hard to um, have a global picture of who is what and what is doing which. So we have these possible kinematics with from Bacri-Lévy-Leblond, which completely organize all sort of contractions coming from that you should always think are coming from ADS or de Sitter, and you get them by either doing the Galilean contraction that we know we have sort of more intuition about it, where the null cones opens up, or the Carrollian contractions, which is in some sense more less intuitive, where the null cone degenerates into a line. And the main message from yesterday in how all of this might have to do with flat holography is that in the very same sense that in AGS you have the same group. Okay, so this is just classification of groups, but in fact some of these groups are the same. They can be isomorphic. For example, these ones are the same. So in the same sense that in AGS CFT correspondence, you have the same groups playing two roles at the same time. At the same time, the group of isometry of AGS and the group of conformal transformation of the boundary. Well, the Poincare group plays two roles at the same time. Well, it plays three roles at the same time. It's at the same time the group of isometries of Minkowski space. It's also the group of conformal Carrollian transformation of the boundary, and this you can really get by, so again, maybe I wasn't so clear yesterday, but I really want to emphasize this 100%, is that this limit in the bulk induces on the boundary the Carrollian limit of the conformal boundary. It's an exact statement. And when you take this limit, you get the conformal Carroll group, which is again, it's just a fancy name for Poincare. It's just like conformal group. The same group you're interpreting in different way because it's acting in a different space-time. But also, this same Poincare group can be understood as the isometries of this extended boundary at time like infinity, which I call psi, and which then you realize the same group as being Carroll AGS. So the statement is that here, in fact, Carroll AGS as groups is the same as the isometry group, as the same isometry group as Minkowski space. Very good. So, please.
There is a mapping among the Carroll and Galilei. You exchange T by X, as one can see already from the figure. If you were in 1 plus 1 dimension,
that's right.
We have an isomorphism, but not. You map a Carrollian theory in a Galilean one.
Yeah.
You have central extension. That's the
Yeah. So maybe, I think, something in the direction of this comment is that here, I think this is really, you have all the possible kinematics when you're in higher enough dimension. When you're in lower dimensions, you have some stuff which happens. You can have isomorphisms which appear, groups which you think are different actually are the same, as you're saying, or...
in higher dimension, still you can map a Carrollian theory
Mm-hmm.
in a Galilean one. Maybe you're not convinced, but
yeah, but okay. I mean, at the level of geometry in 1 plus 1 dimension is clear because you have lines in both situations, but in higher dimension it's a lot less obvious that this is the right perspective. But I do see what you mean. Yeah.
Mm-hmm. You could do it in the sense that your gate fields, your generators, you change P by H, and this has associated with Gaussian gate field, and you can pass from a Simon theory with Galilean to Carrollian.
Yeah. So again, maybe something that goes in that direction is there is one thing is classifying the groups, and one thing is classifying the homogeneous spaces. And so you can have the same groups, and this is what's happening here, right? We have the same group of isometries, but the space-times are different. So in that sense, in 1 plus 1 dimension, you would have an exact isomorphism. Yeah, the space are the same. Yeah. So that was this is the second possible confusion arising in the literature, is that So this is the classical name Carroll coming from Lévy-Leblond as contraction of your kinematical groups. But also people use in the literature as Carroll's group of Carroll symmetry any groups which is preserving this sort of object. And then, as I explained, this is one way of a terminology for this is that they are Carroll symmetries of the weak structure, but then these things are infinite dimensional. And they are infinite dimensional because on the base space, you're going to have isometries essentially of this H. But now you have in the fiber, there is no structure, but this vector field. So you can super translate along the fiber and do whatever you want. Yes, so what was your comment?
My comment is that if you consider electric Carroll particle with energy different from zero, and you look for the most general point transformations, you find that
Okay.
In terms of mix, do you have a name for what you also require
Yes.
to preserve the inaffinity of n?
No, yeah, no. This okay, yeah. You could try some other stuff. Yeah, yeah. So, so yeah. So that, yeah.
Isolated horizons, that also plays an important role. So in this perspective, it seems less important.
Okay, so this actually this is what I want to say here. So yeah, these are groups as coming from contractions. These are groups coming from the fact that you want just to keep the weak symmetries. If we want BMS, because this is definitely not BMS, as this is no point. If you want BMS, you need to look for, because, and the reason why is that it's not conformal. BMS would arise as an extension of the conformal Carroll group, so you need to require, maybe you, I think you already probably said this, Simone, but let me just emphasize this aspect. If you want BMS, then you need to require that the conformal Carroll structure is preserved in this sense. And you could even do other generalization by tweaking this number. There are all sorts of generalization you can try to do. Maybe you don't want to preserve the metric, then you will get super rotations. Well, generalize BMS, all these sort of things. There are all sorts of games you can play from this. But I think the starting point is always weak versus strong structure. You have some weak structure, which is too degenerate, gives you infinite dimensional groups. And then there is a much more rigid structure with a connection typically, which lands you on one finite. And this is always the same, whatever you do. I mean, this is this pattern will come back. I don't know if it's a good name. I mean, this is BMS. I think when you see this is BMS or something. Or, well, when it's BMS, it's BMS. Otherwise, it's. I think in practice, when you discuss with someone, you have to write down what he means because you never agree on the terminology. I think this is rigid. Everybody agrees that these are the Carroll groups. BMS is rigid, and then there are all sorts of names here. So yeah, yes. No, no, yeah, I'm just. No, I mean, yeah, indeed, this would be for Carroll. For Carroll, ADS, you would add hyperboloid. You could look for non-trivial topology, right? I think nobody does this, but you could look for non-trivial bundle, play with these sort of things. True, I mean, you could have for a sphere, but I mean, there is worse. You could be looking for non-trivial fiber bundle over a sphere, right? They exist. You take some crazy manifold, a torus, and you take some non-trivial line on it. You could do that, would be a Carolian geometry. You could even imagine that your null time is just running around in a circle like this. You know, nothing really prevents looking for this sort of example. Nobody really does this, but you can have much more fun. This is local coordinate statement. You can try to work out global features. Okay. So mainly the point was fixing names because as Simone pointed out, there is all sort of names and yeah, different terminology in the literature. So and also clarifying this point. So now the question is, where could you go with this? So I'm going sort of a list. I'm going to list what people have been working on in the field and try to emphasize the direction I'm going to choose and why. The choice here, I have to make some choice on what I want to cover, and there is not, and what I cannot. So something that you can try to do from this is try to look for flat limits of ADS CFT. Yeah, so this is one thing you could try to work out. It's very subtle in many respects. First of all, as I say at Scry, you need to make a choice. This limit is not completely unique. You need to make some choice along the way. And one difficulty is that also in AGS, you have the cosmological constant playing the role of an infrared cutoff. So the infrared divergences are not so much of a problem, but in the flat limit, you don't have this cutoff, so infrared divergences are going to smash to your face, and you're going to have problems. And so defining the limits is very not obvious, and there are all sort of a lot of work in the literature, but still it's a obviously interesting question, and this diagram really suggests this, so there's been a lot of work trying to do these sort of things. Then you could try to just build up Carrollian field theory, or even conformal Carrollian field theory, Carrollian field theory. From bottom up. So you just write a field theory and then try to quantize it, try to work out thermodynamics, these sort of things. Turns out that in practice it's very difficult. People have tried all sort of examples, it's not that easy. You can, so thermodynamics seems to be very badly defined. And you all, yeah. So, and probably most recently there's been progress in that direction. There are new examples of Carrollian field theory, quantum, right? I mean, what's interesting is this will construct some quantum Carrollian field theory. And the most recent result, which I personally think probably is a new interesting development, is that people have been constructing this quantum field theory by discretizing the Carrollian field theory. So you take your Carrollian manifold, you discretize, and then you quantize the theory. There you can sort of make sense of the theory in the discrete setting and try to work out what they are. It turns out that the continuous limit is complicated, and as you expect, because as I said, the usual quantum Carrollian field theory you always find difficulties when you try to work them out. So that's another, and I mean, obviously here the idea would be that this should be meant to be a dual field theory to Minkowski space. But again, this turns out to be hard to work out. But still, progress are being made in that direction. So I feel this is exciting. Some other things that people are doing is fluid gravity correspondence. So in ADS CFT, there is a sense in which you can map in the classical limit a fluid on the boundary with the gravity in the interior, and here you can investigate the notion of Carroll fluid, and this has been quite. There's been a lot of work in trying to make sense of this. In particular, this Carroll fluid, they also appear on horizons of black holes. So you can, what this means is that you can interpret Einstein's equation on the horizon or Einstein's equation at Scry as being the equation for the energy momentum tensor of a Carroll fluid. That's another interesting, promising direction. Another thing you can try to do is, a bit like as Tim discussed the other day, is you can try to do Fourier transform, and I'm going to explain why it's natural. Maybe you've seen this before, but I think you need to recap all of these things. So, and try to investigate, like this would be like trying immediately to work out the dual field theory, but on the other side, you can start from Minkowski space, start from the scattering amplitude, and try to investigate the S matrix in a Carrollian-friendly basis. And so just like Tim explained, you take your usual amplitudes, you Mellin transform it, and you try to make sense of it as a Carrollian, celestial amplitudes, and you can actually learn something about this. You can try to play the same game in the Carrollian basis, and it's been investigated. There's been quite a lot of work in that direction, also more recently. But what I want to do today, so there is no way I can cover any of this really, but what I want to do today is something a bit more, maybe I think more basic, but I think something that we have to face, is the fact that what I'm going to explain today is, okay, first of all, what does this work, what makes this work, is the fact that Now, this was at the level of group on space, but you can make this dictionary work at the level of fields. And I'm going to recap this for you today. So massless fields in space-time, they are going to be encoded as Carolian field at scry, and massive field in space-time, they are going to be encoded as Carolian field at ti. Now, from this, you get a nice dictionary, but there is more to it, as I will explain, and that's going to be the main message from today. The reason why you want to do this, and this is an important conceptual step, is that once you are realizing your field, your space-time usual Poincare fields as Carolian fields, what you realize is that they live to BMS representations. And this you could not see, you can't really see that in a natural way from space-time, but in Carolian geometry, the Carolian fields will realize geometrically BMS representations, and I will discuss a bit of BMS representation, and that's going to be my main message today. Well, that's, I think, a reason why we should be, one of the basic stuff in ADS-CFT is a dictionary between fields on the boundary and field in the bulk, and this dictionary is realized by the fact that you have the same representation. They are on different space, but they are the same as representations. So, and in Minkowski space, the group of asymptotic symmetry genuinely is BMS. So we should better, if we ever, it seems that if we ever want to genuinely understand holographic dictionary for asymptotically flat spacetimes, well, we should better understand how BMS representation theory works and how it relates field on one side or on the other. This is the direction that I want to take today. And again, my message in relationship with Carroll geometry is going to be that BMS representations, they are very nicely realized as Carroll fields, while they are much, much more complicated to conceptualize as Poincare, as a usual, in terms of usual Poincare field. Okay, so that's what I want to say. Any question on this? Yes, please.
So, in the last point where you talk about investigating the escalation in the world,
Yeah.
so it would seem as if massless and massive fields, they both live on
That's right. Yeah,
boundaries.
that's right.
So you have like two different field theories for both.
I think, well, yeah.
Is there like a link?
How to link the two boundaries. So, okay, I think it's a very important question. So indeed, it seems that this is going in the direction that genuinely the boundary of Minkowski space should be time like infinity plus cries, otherwise you'd be missing some fields. So actually, in the flat case, meaning if you're working with Minkowski space, there is a sense in which you can genuinely pack them together. So in the curve case, it's much more complicated, meaning if you are trying to deform Minkowski space. But one thing you can do, for example, you can always think of this space as being the boundary of this one. And this will work. So the hyperboloid, the boundary of the hyperboloid is a sphere, and the boundary of ti is cry. And in the flat case, this is a genuine identification. They are genuinely the same. So you could try, but I think this is an open question whether it's a useful perspective or not. But you can do that. There is a sense in which you can think of massless field as living on the boundary of this ti, and massive field living in the interior. I don't know. I don't think no one really pushed. The problem you see is that this works in the flat case if you're trying to deform this in the curve setting. The problem is that there is no way it can work because ti has to be very localized at time like infinity, while somehow scry is going to be deformed. The causality prevents such an identification in the curves case. But in Minkowski space, because precisely you have a group of symmetry, the boundaries are very rigid, and there is a sense in which you can think of one attached at the boundary of the other one. But I think it's at the same time a very compelling picture. At the same time, in the curve setting, I think it's slightly misleading, and you should not take this too seriously. But yeah, definitely part of the question, part of the difficulty, clearly in Minkowski space, is that you have these different boundaries and points not playing the same role, and it's part of the concept, definitely part of the difficulty. Okay, and I should say also, usually the way you treat, in the literature, the way you treat this difficulty is you just consider one. Precisely here, I'm trying to present this in sort of a unified manner, like massive fields and massless field as somewhat the same structure. And then indeed, as you're pointing out, you're forced to ask yourself, how do I deal with, can I deal with all of this in one unique Carolian geometry? Okay. So let me now just review for you how we construct Carolian fields, massless field as Carolian fields. So what do I want to erase? This one. Okay. Okay, so we take our, I'm just going to work out scalar field, and then you'll have to look in the literature on how to do this for any spins. Everything works the same really, but I don't want to bother with indices. So we take a scalar field, so phi of x, such that box phi equals 0. Then we know we can Fourier transform this and solve it. So yeah, let me not. And now what we want to do here is take BMS coordinates and send and go to r goes to infinity and see the asymptotic data of this field as a Carolian field. And so let me remind you how you can do this. So first of all, you play the little game of rewriting this momentum. So it's massless momentum, so it has to be of the form p mu equal omega of q mu. I'm going to write it as zeta bar. Yeah, and q mu here is this important object, 1 over square root of 2, 1 plus modulus of zeta squared plus so real part of zeta, imaginary part of zeta. And then you do this change of coordinates, and you can rewrite this integral as follows. So it's just a change of variables at this stage. Right, so this d zeta bar. It's I omega q mu of zeta x mu plus complex conjugated. Good. Now, so we are on the way of taking the limit at scry, and for this we need to introduce BMS coordinates. So x mu equal u plus yeah. So the way to actually write it is to write it as u 1 0 0 0 plus r, and then this is q mu of z. So this is a version of BMS coordinates. So if you're in this coordinate, you can check that the metric, so these are BMS coordinates. And here I chose them in such a way that the metric on the boundary is going to be flat. So if you do the computation, plus dx squared plus dy squared plus z squared, you will find that it's minus 2 du dr plus 2 r squared dz bar. Okay, so this is the metric. And now we are all set. We are going to take r to infinity. So you plug this x mu in here, and you take r to infinity, and you take the saddle point expansion of this. Why do I have the minus u squared? Yeah. Okay, maybe I should have. Yeah, because I'm choosing this BMS coordinate system where the metric is flat here. So it's a. Even there are many. Yeah. It is, but no, it's not the same as everything. You see, it's just that usually in front of du you have the scalar curvature of the boundary metric, right? In full BMS expansion, and here the scalar curvature is 0, so this term is 0. Okay. No. They are flat boundary coordinates. I mean, you can choose. Maybe I should comment on this. You can choose any coordinate. There are many BMS coordinate system because you can. There's always conformal invariance on the boundary. Here, I'm choosing one where the boundary is flat because it's going to trivialize a lot of expression. I will have factors that I don't need to carry. Yeah, choose a point. It's just a patch. I'm choosing a patch. So there is a point at z equal infinity. So it's a sphere. Okay, but I mean, I'm just taking out one line. So it's stereographic coordinates. So I have the sphere. I'm putting stereographic coordinate on the sphere, and there is a point at z equal infinity. And whenever you are worried about the topology, you have to ask yourself, how is my field behaving as z goes to infinity? What's going on here, etc., etc. Or you change coordinates and you go on the other side of the sphere.
Everything is fine. It's just that there are some results about the
Sure.
that require the topology. And so one whole.
So my take here is not that I'm changing the topology, it's just that I want to make computation as simple as possible. So I'm just using one patch, very simple patch, with a very simple coordinate system. Whenever we need to be worried about topology, and from time to time you need to be worried, I agree, then you check, in practice, either you change coordinate system or you go as z goes to infinity and you look what's going on here, these sort of things, okay? But it's just a choice of coordinates for me, where it allows me to have expressions which will look nicer, and I won't have to carry metric. I mean, you could make this very fancy and very abstract by leaving any metric, working out conformal, trying to work everything in a manifestly conformally invariant way from A to Z, but that's not what I want to try to do here. I want to try to be very explicit just because, and to see in real money what the Carroll field looks like. Yeah, so you take this thing now, and you take r goes to infinity. As r goes to infinity, these things oscillate, and then you can apply a saddle point approximation. And the result is that the field goes to 0, pi over r, integrate, so this goes to 0, but then the field which remains is the following. So you have a of omega now of z and z bar, because the saddle point approximation localized this integral on the z coordinates. So now it's a of omega z exponential minus I omega u minus a dagger omega z bar of I omega u. Now, so plus a term going to 0 at infinity, so plus O of r minus 2. And this is what you want to call the Carrollian field. So it's the asymptotic data of the scalar field. So I'm going to use different letter. It's phi u z z bar. So it's field living at scry now. And one thing is that since, so coming back to actually Simone's question here, it's of course I'm choosing a coordinate system. And some a point where you should be worried is because when you define this phi u z z bar, you need to multiply by r. Multiplying by r means that this field is not going to have a weight. It's like in AGS-CFT. In AGS-CFT, the order at which your field arrive gives you a conformal weight on the boundary. Here's the same. Because it's arriving at this particular weight, at this particular rate in R, it means that the Carrollian field has now conformal weight on the boundary. So Carrollian field with conformal weight. And then this depends how you count conformal weight. So for me, it's W equal -1. But if you count in type of ADS-CFT language, it's delta equal 1. This is the same, it's just different. This is like Penrose, Newman-Penrose type of weights, and this is usual CFT weights.
Sorry, and the R are nodes from the Hessian, the standard approximation?
Yes. Yeah. Yes.
Which equation of motion verifies this?
No, nothing. This is completely, this is the scattering data of the scalar field, so there is no equation of motion whatsoever.
Maybe you could do the limit, the Carroll limit of the equation of Langorban equation, and that it will probably be, well, I know that the linear second derivative
Yeah.
respect to time
Yeah.
minus
Yeah.
m squared, and I was thinking, is this phi or not?
No. No, I mean, genuinely, so, you should think that you have a scalar field. Okay, this is a scattering problem. Let me draw a picture for what's going on here. So you have Minkowski space, you're solving box of phi equals 0. So usually one way you can do this is you take initial slice and you take your initial data here. So phi restricted at t equals 0. And then you know that you also need momentum, pi restricted at t equals 0, to evolve that equation. Now, this field here, the Carrollian field, is the same data, but along scry. So this is the scattering. You should think of it as scattering data. This is the scattering data for the but it's a different type of problem. It's a null problem. So mathematicians call this a characteristic problem. And when you're trying, I think Simone talked about this, right? So and when you're trying to solve something from a characteristic problem, you don't need momentum. You have just one function. So there is no field. From the point, if you're trying to impose the field equation you want here, you would get a trivial solution in the bulk.
If you do the limit
I
there,
know.
Carroll limit, and you still phi, you get
That's right.
second derivative with respect to time squared
Yeah.
equal to 0. What is this phi?
Yeah, it doesn't seem to work like this. I agree with you, but it doesn't seem that this Carrollian field comes from the Carrollian limit of an on-shell field on the boundary. That's, yeah. This is maybe sad or surprising or maybe, yeah, but that's, yeah. Again, if you're trying to impose a field equation on this, you're going to practice the degrees of freedom in the interior. So you should not do this. Yeah. Yeah, no, it's an important point. Okay. So what I want to emphasize here, what did we gain? Okay, this is a Carrollian field. Now we know the Poincare group act here. So let me, yeah. And let me remind you how the Poincare group acts on this field. And then we'll discuss, again, what's interesting here is, okay, unfortunately, or maybe fortunately, this field is not the Carrollian limit of a conformal field in on the boundary of AGS. But what's interesting is that this is a BMS representation. This is what I want to discuss now. But let me just, before that, remind you how translation acts. Okay, so the field carry carries a representation of ISO 3.1. And the way it works is just that you have vector field X, and you have your translation, Q, mu, so it's a Carolian vector field. So it's X, U, Z bar. Translations are realized as in terms of this Q mu, Z bar, du. Well, and then you also have the Lorentz group, or you can even work out a complicated group. So this is the divergence of a vector field, Z bar du plus Y Z dz plus Y bar Z bar dz bar. Where here I'm always going to think, but if you want to weaken this, you can, that this Y Z dz is an element of the Lorentz group, which means that it's quadratic in Z. Okay, so this is Lorentz. And this is translations. And now it's clear, so I mean, from the construction, it should be clear that this phi u z bar is just a usual function on the boundary, just with a weight. So this vector field on the boundary, it's represented as a Poincare group just by the action of this infinitesimal vector field. Sorry? No, in this case, it's completely faithful. Yeah, because, I mean, you see, this is just a rewriting of the initial representation, right? Phi of x was the massless representation of the Poincare. Here is just the same one, just you're thinking of it as living on the boundary, but it's the same representation, really, right? Yeah, so the field transform as it should to be a conformally weight one field. So you have Lie derivative of, so how am I writing this field with little phi, like this? And then you have this term which accounts for the weight of phi. Okay, so it's usual Lie derivative, and then conformal this. Okay. And therefore, in particular, translation as follows. In particular, T mu acts as, this is what I want to. Woo! Or if you would rather, perhaps we should rather work with the Fourier modes, it's just an exponential, and this is the same. Okay. So again, what did we do here? Well, not much, because so we took our field in the bulk. It's a representation of the Poincare group. We take it, yes.
This phi,
Yeah, no, sorry. So this okay. So it's just genuinely just a translation in U. That's all it is. Yeah. So thank you for no. Yeah. So again, this is the same field. Just we are thinking of it either as a field on the boundary or a field in the bulk, and now it's the same representation, and we are explicitly here realizing the dictionary. Now, the surprise, I think that should be a surprise, is that in fact, this extends to a BMS representation. And this is, in fact, due to Sachs in the initial abstract sense. But let me... So we can modify this now, so surprise. So I'm just going to state how it works, and then we'll discuss a bit of BMS representation and how it fits in this. Extend to a rep of BMS. So why? Well, from this perspective, it's rather clear, because BMS, what is BMS? BMS is X, U, Z bar. But now, instead of having these translation bits, I have any functions, curly T, T is Z bar, and then all the rest is the same. Plus, double dot, du, plus, YZ, DZ, plus, bar, Z bar, DZ bar. So, yes.
But maybe it is not so strange. In the 98 Longi Materazzi,
That's right.
somebody realized,
Absolutely. Yeah, yeah.
I think it's good giving credit to them, using another basis. But already with it.
Yeah, yeah. But Longi Materazzi also, I mean, this is, I'm crediting this idea to Sachs, so 62. And I think Longi Materazzi, they did the same for massive fields, and that will be the second part. I will do it for...
Milan for matters one, same philosophy.
True, true. But I think Sachs, I think really Sachs was already pointing that this is the case for, well, I mean, depends what you, yeah, yeah. For massless field, I think it was realized very early on that indeed it's a BMS representation, yeah. But for massive fields, definitely Longi Materazzi were the first, as you were saying, yeah. Yeah, yeah. Even though, I mean, in all these things, in Longi Materazzi, clearly, certainly what they did not have is the understanding of this in terms of asymptotic symmetries and asymptotic data. Definitely, they were not thinking in these terms at the time. No. No, no, they were not thinking like this, no. I mean, it's a very clever paper, but it's sort of guess that the BMS representation for massive fields just from intuitions. But they are not thinking of this as, you know, the action of asymptotic symmetries or anything like this. I think this came much later on. Maybe that's what, this is the new bits in this perspective, is thinking of this representation theory statement as coming from the action of asymptotic symmetries, and therefore geometrizing this. I think that's my message. Let me write this, and let's say what maybe Carroll has to tell us. So yeah, I mean the representation is the same, and therefore now you have, and in particular, super translations act well, it's exactly the same. So now you get it for free. But you need to realize that from the perspective of the bulk, it's very not obvious what this is doing. I omega to Z bar A omega Z bar. I need something else now. Yeah. Okay, so let me emphasize one aspect, is that here it seems obvious what you have to do is you just replace, now that you're at scry, it's clear that super translation is you're just replacing this U translation by this translation by super translation with any dependence in ZZ bar, not just usual translation dependence. But if you're doing it on the Fourier modes, it's much less obvious what you're doing. You're multiplying your Fourier modes by a T. And if you think about it, what it means is that this is geometrical. It's just a diffeomorphism at scry. You You have your field at scry, you act with the diffeomorphism is BMS. So this is a geometrical representation of BMS, while if you are trying to understand this from the perspective of the bulk, this is very non-geometrical, it's very non-local. I mean, there is no sense you can realize this action on the field as local diffeomorphism in the interior. So in particular, it's not, you should not think, because it's not correct, that what you're doing here is you take BMS on the boundary, you extend it as a diffeomorphism in the bulk, and you act on your scalar field in the bulk. That would not work. Okay, if you take a solution of box phi equals 0, I think it's clear that it is, but it's not. If you take box phi equals 0, you take phi, you act on phi with a BMS symmetry, it will not be a solution of box phi equals 0 anymore. It doesn't work.
It should be a solution of super-translated box.
Yeah, for another space-time, right? If there is another space-time, sure, but then you're not saying anything, right? So here it's genuinely constructed. Absolutely. But here you're genuinely constructing another solution for the same Minkowski space, you see? This is another solution, because it's just Fourier modes for the same Minkowski space. Yeah.
But wouldn't, I mean, for the same Minkowski space by which your constant U are not by the cut.
No. Well, but I mean, no. Look just at this. Forget about scry. Just look at this one. This is another solution of the scalar field equation.
But when you say this is another solution, you're still thinking of this as being the free data scry of that solution.
This is the new free data.
Right.
Yeah, and this is in Fourier modes what you've been doing. It's another solution, and what I'm saying is that these two solutions, in the bulk, they are not related by any local transformation. It's a very non-local relationship. It's local at the boundary. At the boundary, you just acted with the diffeomorphism in the boundary, but inside, you did something very non-local. And it's just the statement that propagation, mixed up the journey. They are both solutions on the same Minkowski space. So in this sense, this is a symmetry, obvious symmetry. But again, I think that's what I mean. This is what we gain by going to the Carrollian boundary, is that now the symmetry is local, geometrical on the Carrollian boundary, while in Minkowski space it's not. Okay, so let's do a little bit now of VMS representation theory and try to see what this is telling us from that perspective. Because here we just realize that our field is a BMS representation. Yeah, by the way, I should say it's unitary for the same usual norm that you like for Poincaré. So let's do a first glimpse of BMS representation. So something that we are getting is the notion of supermomentum. So in usual representation theory of Poincaré, you define momentum. So usual momentum, usual momenta, I should say. So P mu, they are defined as dual elements to translation. So in Poincaré representation theory, it's so obvious that we don't even think about it, but this is the right perspective. So it's dual in the sense that you take T mu, and this P mu you contract, and you should write, you write the contraction like this. It's P mu, T mu. Then wave functions, what are these? Well, they are function on the mass shell. Usual wave function, are functions. So let's say A of P on a mass shell. Okay, so this is what the way we are used to think of it as physicists, but genuinely, if you look at the way Wigner would think of it, or even Weinberg, the fancy way of saying this, which is going to be useful for BMS, is that this is the orbit, a mass shell is an orbit of the Lorentz group. In momentum space. In the space of momentum. And then translations act on the wave function as, well, A of p goes to I p t A of mu. Good. So what's the parallel statement for the BMS group? Well, in fact, since the group are very similar structure, they are both semi-direct product. You have a clean dictionary. So here, by the way, I'm going to follow the work of McCarthy, who is a mathematician who classified all BMS representation in the 80s. So I think actually that was before Longhi Materazzi also. If we are, I think the McCarthy's work on BMS representation, they were in fact before Longhi Materazzi. So no, yeah. Well, they pretend, yeah. Well, I will explain. Well, this is very similar, but yeah, I will. Okay, so super momentum are dual element to super translation. So I'm going to write them as curly p z bar. They are dual elements to super translation. And what that means is that you need a pairing like this, So super translation is t z z bar, and the dual act as follows. You take t z z bar, and you map it to curly p curly t. But now this space of super translation is infinite dimensional now, so the pairing is an integral. So I'm going to write this with dz squared. So let me use another letter. Zeta bar, zeta bar, and d zeta curly p of zeta bar, curly t of zeta bar. Yeah, so you should think of supermomenta as being supermomenta, equal, you should think mass aspect, only mass aspect. Or maybe even better, or BMS fluxes, BMS charge fluxes. Okay, so it's a function on the celestial sphere, but the conformal weight should be such that this object has weight 0. So this is weight conformal weight 1. So this is delta equal 1, minus 1, sorry, minus 1. So this should have delta equal 3 because this guy has delta equal minus 2. Now, wave functions, I'm going to keep that. Yeah, please, please, please. Please.
Because if I'm thinking of zeta
Yeah.
as coordinates on the sphere,
Mhm.
as coordinates, when I do a boost, nothing happens. So I would think
Okay.
that
No, no, that's right. Okay, I see the confusion has to do with the previous thing. That this you should not. Okay, I'm working, in this coordinate system, which simplified its expression, but then makes it confusing. Where h is dz bar. Okay, so that's. But in fact, okay, in general, this should be h z bar with here any metric dz bar, and then you should really take, this is what this should be. This is the object which is conformal weight minus 2.
Okay, but if you do it this way, then I don't understand anymore the conformal weights of the P and T. Because now T has conformal weight minus 1,
Yeah.
when it's a function of coordinates that have conformal weight 0 in my head. So now, if it is a function of coordinates that have themselves conformal weight, and this is an arbitrary function,
No, no.
how do you understand which?
Here, this is just a local coordinate statement. I mean, the right abstract way of saying it is, I have a metric. This is just the volume form of the metric. This is what you should write. And then it's P and T. That's what I mean. And here I'm just writing this in a coordinate system where this looks trivial and you don't see it anymore. Yeah. Yeah, 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 yeah. Yeah. Yeah, again, this is where I'm using coordinate system to simplify expression, but indeed, conceptually, you might get confused. Yeah. Yeah, you should really write the volume form. Abstractly, what you should write here is the volume form.
Okay, just final stupid question also. Would you agree that if you want to recover the correct transformation laws of your supermomenta under boosts, so to get the closed algebra identity, you need to include the square root of h in it?
Yeah, yeah.
And so think of it as a delta equal 1 as
Yeah.
opposed to delta equal 3. If you want to recover, if you want to close the full DNS algebra, which is what otherwise you would miss.
Again, you're right. You want this object certainly to be in fully Lorentz invariance and fully, so if you want to do this, you're right. You need to be extra careful by what you mean by acting with Lorentz group, or equivalently what you mean by changing coordinates. Here, I'm really writing this stuff in one coordinate system, and what you should be worried is what does that mean? I mean, I could change coordinate system. What do I mean? And the abstract way of making this correct is saying, okay, this is not a volume form. This is the weight minus 2 volume form canonically defined by the conformal geometry on the sphere. And this is a weight 3 density on the conformal sphere. This is a weight minus 1 conformal density on the celestial sphere. And then it's yeah.
Now, if you look at the algebra between your P conformal weight 3
Yeah.
and the boost,
Yes.
I suspect you will not get
You will.
what you would expect.
No, you will.
To include the square root of h in what you would P in order to get P with boost.
You will. No, precisely. You will get with that tree. You will get the transformation rules that you want. I think you just need to be. You need. Maybe the confusion is maybe just what we mean by a conformally weighted object. I think that's just just the basis of this discussion. But I mean, so there is a sense you can write it down explicitly in which this guy transformed the way it should under the action of the Lorentz group if it's a conformally weighted 3 point, with weight 3. But yeah, I agree that whenever you're working with densitized objects, you have different conventions, different point of view, and you might get confused in the dictionaries. But yeah. Okay, so wave functions. So BMS wave functions. So BMS wave functions. They are also. I'm going to write something and then we discuss. They are also. How did I write it? Are functions. But now it's going to be A of curly P on the space of supermenta, but also they need to be on shell. On shell. On shell. And here, what does that mean to be on shell for supermenta? It's very unclear, but what you're supposed to understand is read this other definition. They are on a given orbit of the Lorentz group. in the space now of supermomenta. And then once you're here, well, super translations then act as follows. Super translation. They act as, well, similar. So you have curly A of curly P now, super momentum, sent to exponential of I, but now you need to take this bracket of super translation with super momentum of A of curly P. And I want some minus I think, in my convention. Anyway. Okay, so that would be the general statement. So McCarthy, what he could prove is that with this, this is the induced representation method for BMS group, and there is a sense in which you have them all. So here it's rather subtle because when you want to classify BMS representation, and you need to be careful about what you are looking for. You want to classify something, so you need to define exactly what you want to classify. What is subtle here is the fact that the BMS group, we are thinking of it, for us, it's obvious what it is, but in fact, when you're doing it from the perspective of representation theory, you need to also say what is the topology you want to choose on the BMS group. That's going to matter. So one thing, and the topology of what you mean by topology is exactly what is the functional space of super translation you want to consider. Are you thinking that those curly T, Z, Z bar, they are C infinity functions? Are you thinking that they are square integrable? Are you thinking that they are maybe in some Sobolev space or something like this? So you need to say it in order to run a classification argument for BMS representation. So in some cases, it's fully classified. In some other, the classification is less constraining. Anyway, there is a sense in which these are all BMS representations. And now I erased, no, I keep this, so now we can compare the two and see which representation this is in. So now we compare this with this, and what we find is that we find the super momenta for the massless representation of the BMS. Well, now we are interpreting this. This is the Carrollian field representation as BMS representation, and we see that for the two things to match. So for this and this to match, we see that the Carroll representation is the BMS rep with curly P. I'm going to call it curly P hard of, so let me make sure. No, I should not have erased the integral, so let me, this. So I want a delta functions, but let me make sure this is crap. Yes. Minus I integral d zeta squared of curly P zeta bar to zeta bar. So if you want the two things to match, you need the super momenta to be a delta function omega delta z minus z. Okay, so this is the statement, is that this, if you want, and you should think of the Carrollian field living as cry as being a BMS representation. What this means is that this is curly T contracted to the super momenta, but super momenta should be a dual element. This dual element is a delta function here. And this is, then now you should think of A of omega z bar as being a function in super momentum, A of curly P, but now it's on shell in the sense that it's evaluated on curly P curly P equal omega delta Z minus Z. So this is the mass shell of supermomentum inside the supermomentum space. And this, you should think of your usual field in Poincaré as being on shell in this sense. And now super translation, these are the same representation, meaning the super translations act the same way. Okay. Okay, is there any question on this aspect of BMS representations? No? Yes? Mm-hmm. Yeah. So you see, as I explained, the recipe for constructing a BMS representation is that you have a way BMS wave function is a function in supermomentum space. So this should be a function on an infinite, crazy, infinite dimensional space. But for it to be irreducible representation, just like in Poincaré, it should be on shell. So living on some very tiny subspace inside this crazy infinite dimensional space. And again, the fancy way is that it should be on an orbit of the Lorentz group. Here, so here again, the wave function should be a function on supermomentum space, but now you are restricting it on this mass shell. This is a very particular submanifold of the space of supermomenta. And once you restrict your wave function to this, well, you should think that it's zero on any other supermomenta. Then effectively it just becomes a function of omega z and z bar, which you identify with this guy. But now super translations, well, they act like this. And since in fact this A is A of P with P being this, well, this is the transformation that you get. Yeah. Yes. Yeah. So the relationship with Carroll geometry, maybe that's why this way. Okay, so at some level there is not. So you can just, and this is, as Joachim was pointing out, for massive fields, you could even guess that without any going to scry. So then, you can think of it as just as a statement that from your usual Poincaré field, you can extend this as a BMS representation in terms of the Fourier modes, and then you just compare with McCarthy's result, and then this is the representation. Now, if you can do this, but then you don't have any geometrical realization of the BMS group. It's just an algebraic fact, and that's it. What the Carolian field allows you to do is that now you Fourier transform this guy, you get a field that's cry, and now what is this representation? This one is geometrically realized by taking the asymptotic symmetry group and acting on the Carolian field with diffeomorphism. So that's the message, is that BMS representation is an abstract statement, but the Carolian field is geometrically realizing this representation as just the BMS group acting as diffeomorphism on the boundary. That's the statement. Because again, this thing from the perspective of the bulk is super non-local, very not obvious what you're doing.
So you're saying that there's no classical realization of this transformation of the phase space of asymptotic free data from the scalar field? You really need this Carolian perspective in order to realization of
No, it's just if you want to realize it as space of diffeomorphisms. I mean, this is the realization. Take a scalar field, Fourier transform, that's it. Nothing more. Now, this is in Fourier modes, but in space-time, this is not the action of a diffeomorphism. It's very complicated. However, on the Carolian data, this is genuinely the action of an asymptotic symmetry on the Carolian data. That's all I'm saying.
But this Carolian data are also what describes the relative classic of the space of the field.
Yeah. Yeah. Well, I mean, another way of saying it is that if you want to realize the BMS group, you need to look to realize it as an asymptotic symmetries. So that's what you should do. Yeah. Yeah, absolutely. Yeah, maybe okay, that's what you were saying. Okay. Okay. So from that perspective, again, Carolian physics or boundaries, they are good because they geometrically realize, meaning in terms of diffeomorphisms, the BMS representations. Okay. So yeah, please.
What are the issues if you try to do the same discussion with superrotation?
Okay, it's a very good question. The issues is this is in this case there is no classification, so there is no general theorem telling you that you have all representation even in some corners. So you can try to do it. Laurent has some paper on that. Glenn Barnish, in 3D you can do this. So if you were doing BMS3, in BMS3 is much simpler because then it's super rotation is just Virasoro on a circle, and Virasoro, despite the fact that it's infinite dimensional and still very hard, there is understanding of representation theory of the Virasoro group. So there you can try to push your understanding and try to understand all BMS representation in 3D and do this sort of games. This you could try to do. But in 4D, with any, let's say, any diffeomorphism on the sphere, representation theory is bound to be very complicated. I think, yeah. For example, yeah. And I think this is to be worked out, like a full, complete understanding. Lawrence is fine. Yeah. Yeah, yeah. You mean with Lorentz group, the action of the Lorentz group? Well, okay, let me. Well, you act as you were saying. Super momenta, you can act on it with Lorentz group. So the action of the Lorentz group is just act on super momenta. You have your wave function, act on super momenta, and that's everything will be perfectly consistent. Sorry, yeah. On the celestial sphere. So you have the celestial sphere. The Lorentz group act on the celestial sphere. Therefore, it acts on super momenta. And this is not what you're asking. No. It will all. Yeah. Well, it will all work out. I mean, this will all. Yeah, it will all work out. Yeah. Yeah. I mean, yeah. It's the same problem with Poincaré, right? You have many groups, Lorentz subgroup of Poincaré, but everything is working out. No, but here there is no U. You see, here is no. Right. So because now U has been spread over omega, it's going to be very complicated. No, that's the opposite. It's very simple now because this is just that, right? All you do is you act with the Lorentz group on this P. So this is just a function on the sphere. You act with the Lorentz group here, and that's all there is to do. Nothing more. See, in this expression, it's clear what you mean. This is a new A. This is A tilde of curly P. So you just act on this guy with your Lorentz group, and this is the action. There is nothing more than that. Okay, and good. So now what's I feel compelling is that the same story goes for massive field. Exactly, step by step, everything is the same for massive field. And we are going to figure out. So in what follows, I will call it this hard supermomenta. I'm going to write them with a straight P, Z bar, zeta bar. So here the statement this is the hard supermomenta for massless field. So hard, let me hard supermomenta. Yeah, for BMS massless field. And now we are going to construct the hard supermomenta for BMS massive fields. So we call them hard because of this statement, because they are the supermomenta induced from a representation of the usual Poincaré representation. Okay, so let's start massive fields now. So now start again with phi of x, such that box of phi equal m square of phi. Phi of x is m squared Now, so now I'm Fourier transforming a massive field. And so here, what? So this is P. Okay. So the way I'm writing it is that P mu. So my notation is that P mu is M P tilde of K, where P tilde is this object. Such that P tilde equal -1 squared equal -1. Now we take by-Schmidt type of coordinates on Minkowski. So basically this is this guy too, P tilde of Y of mu. And then minus dt squared plus dx squared plus dy squared plus dz squared equal minus d2 squared plus 2 squared delta ij y minus yi yj divided by 1 plus y squared dyi dyj. So again, these are by-Schmidt coordinates. And by which we mean that we are this is this. I think a lot of you call it the hyperbolic foliation. Well, it is hyperbolic foliation. And this is the metric on the hyperboloid. And yeah, this is tau. Now we want to take the limit. Tau goes to infinity and see the Carrollian field arise. So yeah, let me do that shit. Let me do it here. Or maybe, yeah.
In principle, now that we are in a massive case,
Mhm.
Logge Materazzi didn't need to take the limit to get BMS.
That's right.
Therefore, why don't you take the limit?
I mean, it's like, you see, that's this. I absolutely agree. You see, why you should take the limit if you want a realization of the group as a group of dimorphisms. But if you just want the representation, you can just work with the in Fourier space. This is the same for the massless representation. You can either work in Fourier space, and then representation is just you're exchanging p dot x versus against this curly p contracted with curly t, and you can sort of, if Longhi Materazzi, sort of guess what's the right curly p you need to choose, what's the right super momenta for massive representation.
Yes, I don't think it was a guess.
Yeah, they did guess. Sorry?
That I don't think was a guess.
It was. It is. They really guessed it. They guess it and then they prove it's correct. That it's a representation. That is.
There's a logic behind that. Okay.
Well, yeah, we can discuss. No, I think.
The question is, why really you need to go to the symptotic?
I think again, if you want, again, what I want to advocate here is that if you want to realize the BMS group as a group of diffeomorphism acting on a field, this is what you have to do. When you're working on these Fourier modes, this is just an action. It's nice, okay, it's a representation, good, but it's not the realization of a group as a group of diffeomorphism. It's not the realization, it's not the geometrical realization of the symmetry. If you genuinely want to realize the BMS group have some group of symmetries on the field, you need to go to asymptotic time-like infinity. There, BMS symmetry becomes an asymptotic symmetry at time-like infinity, and you do see the asymptotic symmetry group acting on your field. So it's a, it's representation, so they are the same representation. One is geometrical in the sense that it's an asymptotic symmetry group acting. The other one is just something that you're doing on the Fourier modes. So it depends what, yeah, depends what you want to do. Or okay.
I mean, just that from the bulk point of view, there's no reason to look at this subgroup of different.
That's the point.
Yeah.
In a sense, maybe the message a posteriori,
Mhm.
not when they did that in '98, that really VMS symmetry is more kinematrix, nothing to do with asymptotic symmetry.
Nothing to, well, it has something to do with asymptotic symmetries, but yeah.
The way they were looking at it, maybe this is your point.
Sorry?
Maybe your point is that they had a way of introducing the symmetry in a way that was completely unrelated to asymptotic.
Absolutely, yeah. Yeah.
In their perspective, this link was not there.
Yeah.
This is what you're saying.
No, but Joachim, it's as if you were saying you like box phi, and then you realize that the solution is a representation of the Poincare group. You could say, oh yeah, it's just a fact. But it's coming from somewhere. It's the fact that you're solving box of phi on Minkowski space. The symmetry group is a symmetry of Minkowski space, and this is why your representation, your field are going to be representation of Poincare. Here is the same. The reason why these things are actually magically a representation of BMS is because BMS act on the scattering data, and this is why those things are BMS. So if you want, it's a geometrical explanation for why this construction works. Also, yeah.
It would be nice. I will be giving a seminar on Friday.
Yeah.
And I will talk about that.
Uh-huh.
Probably some discussion.
Very good. Uh-huh.
But in principle, from their point of view, you have the bulk, and that's okay.
No, but this symmetry is very non-local in the bulk, right?
No, you make this interpretation of
Yeah. 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 No, that's the magic of representation theory, is that it's abstract. You don't need any specific realization. It's just what it is. But then, like in ADS CFT, it's good to have different realization for the same representation. That's what I'm advocating here. The same thing, the same representation can be realized in different way, either as field in the bulk, field on the boundary, and then this is the same representation. So in one way, we are not learning anything, but we are learning something because it's different realization of the same representation. Yeah. Yep. But yeah, maybe that's what you're saying is the full point, is that representation theory does not care about particular representation. That's why it matters. That's why it's important, and this is precisely what I want to advocate here. Okay, so what do we want to do? Now we want to take tau to infinity limit. We take this field, which is now so phi of x, now in this by Schmidt coordinate system is phi of tau and y. And as you take tau to infinity, you have again a saddle point expansion. And it goes like as follows. So it's square root of m divided by tau to the power 3 half. 2 pi 3 half of a of y And so here now we see that it's completely different. It's different. So this is okay. So first of all, the difference is that there is an oscillating behavior, and this will come back to our face when you try to think of this guy as a Carolian field. But naively, you might want to first define this as your boundary field. And really, what this means is that so you see there was a delta function again, and again, what the delta function did for us is identify the wave functions that we were thinking as being on shell in momentum space as a wave function being now on shell but now on the hyperboloid at time like infinity. So the characteristic data for the massive field is just the Fourier modes evaluated on the hyperboloid. But you have to be careful because translation act non-trivially. So you like to think so, but translation, they act as, yeah, and I will, A of y is sent to imaginary parts of I m p dot k t, so mu a of k. So it's a bit more subtle than this, right? You would like to think that your scattering data is just a field on the hyperboloid, but it cannot quite be the case because on the hyperboloid translation act trivially, while here translation do not act trivially. But one thing you can do is now lift your field to this extended boundary tie, and this will solve the problem. And you will as that lift the field to tie equal Carroll radius, which I'm writing as R times H3 with S and YI, and then define the Carrollian field as phi of S and YI. It should be just the following stuff. So now there is a phase which now is encoding the mass and A of Y. Okay, so it's slightly silly dependence on the extra dimension, but so as you remember, translation act on Carroll DS, they act on tie as follows. Well, I didn't quite, in particular. Yeah. Yeah, in this case it is. Very good. Yeah, very good. In this case it is. Yeah, in this case it's on shell in a certain sense. That's right. Well, no, because before there was a U dependence. It was important that to have a U dependence.
But if you take the expression
Yeah.
that you had
Yeah.
in the Malthus case,
Yeah.
instead of being second derivative with respect to S,
Yeah.
equal
M, yes.
will be second derivative with respect to S over the time,
Yeah.
which is radical to zero.
No, but you see, here it works, so I agree. So here, this looks like the Carrollian limit of a Carrollian field on the boundary, agreed. But in the null case, if you take, it would be like saying that the Carrollian field should have no dependence in U. But if you do this, you're killing all the structure of your field in the interior. It's important if you want to have a non-trivial scalar field in the bulk. It's important that the scattering data depends explicitly on U. Should not be constrained by anything. So from that perspective, it's different pattern and structure between massive field and massless field. So here I agree, in some sense, this field is on shell for the Carrollian geometry of the boundary. Here it's a nice dictionary, but for Scry, it's not, yeah, slightly different, yeah. And yeah, let me, I think I just write how translations act, and I'll discuss BMS, how it fits with BMS representation tomorrow in the afternoon. So in particular, translation act Okay, so this depends on K. Okay. Okay, and so I will finish on this. So same thing happens for the massive field. The massive fields do induce a scattering data at time like infinity, or it's almost just a scattering data on the hyperboloid, but not quite, because you want this translation to act. So in order to do this, you need to think of it as a field on this Carolian ADS, which is on shell in a certain sense, as Joachim is pointing out, and then you are genuinely realizing the action of the Poincare group on this field as a representation. And this afternoon, I will explain how this leads to a BMS representation and with the same dictionary and our super momentum, and then we'll try to go a bit further. Okay, thank you. So let's, yeah.